Hi everyone, this is your instructor Ryan. I just wanted to make a video to show you how to do some of these probability problems using contingency tables. I'm sorry about my voice, I'm a little bit sick right now. I just kind of wanted to walk you through some of these and show you how to solve some of these problems. So in your manual this should be review exercise 3.3. Now I'm using a slightly different version of the manual, so for me it's page 68, but it should be around there for yourself. So this is the first problem in the set of review exercises. Should be number 1. Now I've taken some select problems and added my own to try to illustrate some of the ways you can do these things. This thing here is directly out of the textbook and it's called a contingency table. There's a few things we're going to need to add before you can actually get into the meat of doing these problems. So what I like to do, and this is going to really help you out, so I suggest you do this before doing your assignment or even on the test, is to add a little total column at the end. So you'll notice that this is the numbers of people who are obese, anorexic, and overweight in a local town broken down by age. So you've got less than 25, 25 to 50, over 50. You've got the obese, the overweight, and the anorexic, and you've got everybody counting it up. But you're going to want to add these totals because it's going to help you figure out the probabilities. So we'll put a total here and a total down here. Okay. Now you're going to add all these up. So off the top of my head, I think this is what, 80, 90. I think this is 190. And then over here we have 205. Over here we have 15. And then you're going to add these ones up. So 15 and 205 is 220 plus 190, and I'm getting 410 out of that. Okay, and then we do the same with the rows. So 42 and 65, that's 107, and plus 8, that's 115. We have 110 and 80, and 5, that's 195. And then finally 2 and 38, that's 40 plus 60, that's 100. Okay, now you're going to want to make sure that the total here is the same as the total here. When you add all these up, it should be 410, and when you add all these up, it should be 410. So let me just quickly in my head do this. Looks like it's okay because 115 plus 195, that's going to be 310 plus 100, that's 410. Okay. So the first thing you want to figure out, I added a couple questions just to kind of warm us up a little bit. Now, when it comes to the probability, you're always trying to figure out, so when I'm trying to find the probability that we have an obese citizen, it's always out of some total. So we have 42 people who are obese, that's right here, out of a total 410. Now there's some number you can get out of it. I don't have a calculator on hand right now, but you can certainly figure out the probability. Usually I like 4 decimal places if you do that. So I'm just going to add that in up top here. So now you can do the same thing with the anorexic. So you look at the anorexic column. You know what, actually, this is a good lesson. I did that wrong. So that's not 42 because the 42 comes from the people who are obese and the ones who are less than 25. So this is just the people who are obese and are less than 25. What you're going to want to actually do is you want to look at the total number of obese people. So the total number is 190, and there's 410 people in total. So this is going to be 190 out of 410, and that's the probability that in this sample of citizens you happen to be obese. Now you want to look at the number of people who are anorexic. Well, you do the same process. So what I did for the obese was I totaled it up, took the total of just the obese people, and then I took that over top of the total people in the sample. So for the anorexic, the total that we have is 15 people who are anorexic out of a whole 410 in our sample. So the probability that we're anorexic is equal to 15 over 410. Okay. Now we do the same thing with the 25 to 50 crowd. So we're looking at now the probability that you happen to be in this sample a 25 to 50-year-old person. Well, now the difference here is with anorexic, it's in the column, but 25 to 50 is now in one of the rows. So you're going to want to take the total over here instead of, taking the total of the of a column. Now you're taking the total of a row, 195 over the total in your sample, which is 410. Okay. So as you've probably read in the textbook, or maybe not if you haven't gotten to it, we also have these sort of compound probabilities. So this is kind of the subject of the actual exercise. So you'll notice this one now, we're not just trying to find out if they're obese, or the probability that a person's obese in this sample. We also want to find out what's the probability that you're both obese and less than 25 years old. Well, actually, this incorrect work that I've done here is actually kind of correct when we go down here, because if you look at it, we're now trying to figure out the probability that we're obese and, so that's kind of the key word, we are less than 25 years old. And I'm just using notation here to make life a little bit easier for myself. So here's the obese column, so we know we have to be in the obese column, and here's the less than 25 row. Well, we want just the people who are obese and less than 25. So this is going to be 42, because there's 42 people who are obese and less than 25 years old out of the total of 410 in our whole sample. Okay. In B, we're looking for the people who are overweight and over 50. So we're going to look at the overweight column. We're going to look at the over 50 column. All right. Well, we need the people who have both qualities. Well, you're overweight, so you're in this column, and you're over 50, so you're in this row. Well, that means you're going to be right here. So there's 60 people who are both overweight and over 50. So the probability that we're overweight and I'm going to use the greater than sign, 50 is going to be equal to, well, 60, because there's 60 people who are both overweight and over 60, or over 50 rather, over 410. Okay? Now, or is a bit interesting. So, as you've probably read with this one, the or means you're overweight or you're older than 25. So this is an inclusive statement in the sense that it includes when you're overweight. It includes, well, not you, but when the people you're looking at are overweight, when they're older than 25, and when they're both. So what you're going to do, okay, so the probability that we're overweight or older than 25. So now we have to consider both cases. So first of all, we consider the probability that we're overweight. And there's actually a formula for this that you guys can look up, but I'm going to kind of walk you through this and sort of the reasoning behind it, which it does in the textbook as well, but I'm going to kind of proceed in sort of that systematic way. So the probability you're overweight, well, there's 205 people who are overweight out of a possible 410, plus the probability that you're also older than 25 years old. So we want the people who are overweight, the people who are older than 25, but if we take all the people who are overweight and we take all the people who are older than 25, which is actually two whole columns right here, we're actually double counting a little bit, because if we first look at the 205 people who are overweight and then we look at the total of these two columns over here, well, we've double counted this 80 and this 60, this place where we're both overweight and older than 25. So what we actually have to do is we actually have to subtract off the probability that we're overweight and we're older than 25. And again, that's just to to compensate for the fact that we've double counted when we first add up the probability that we're overweight and the probability that we're older than 25. So let's look at what we get. So overweight, this is 205 over 410, okay, plus older than 25. Well, this is actually both these columns. We have the 25 to 50 crowd and the over 50 crowd. So it's actually going to be 195 plus 100 because we're grabbing two rows divided by 410. And then lastly, we have to subtract off the probability that we're overweight and older than 25, the stuff in here, just to compensate for the fact that we've double counted a little bit. So we're going to subtract off, and I'm just going to put this in brackets. And let's put this in brackets too, so we remember to do everything in the right order. 80 plus 60 over 410. So this is going to give us 205 over 410 plus, this is 295 over 40 minus 140, or not 40, sorry, 410 over 410. Okay, so I think what we get here is it's 300, 500 minus 140 is going to be 360 over 410. Okay. Sorry about the awkward writing. I have I'm trying to write this all and hold my paper down so that I don't move it around too much. So it makes it kind of hard to write neatly. Okay, now next let's talk about the people who are obese and anorexic. Well, here's the interesting thing. So if we look at the people who are obese and anorexic, now you might sort of give an argument saying, well, how can you be obese and anorexic just logically? And, it could be. There might be a few people out there. You never know. But you don't even really need that in this case. All the people who are obese are in this column right here. All the people who are anorexic are in this column right here. So even if you might argue that in the real world, maybe there are some people who are obese and anorexic, in just the math that we're doing today, these two columns will never overlap with each other. And we obviously, in the case where we had like obese and over 50, we needed some overlap. So what we're going to have to do is we're going to have to say, well, the probability here is 0, because you can't, in this particular case, you can't be both obese and anorexic. Okay. Now given's a little bit tricky when it says given, because when talking about given, what you're doing is, in all these cases, we've always been over 410, because that's the group of people that we're looking at as a whole. We're saying how many people out of the entire sample that I looked at are overweight or obese or overweight and 25 to 50, etc., etc. But when it comes to being given, what we're going to be trying to do, or at least what it's saying mathematically, is that you're restricting the group of people that you're looking at the probability for. So we want to say that now, if we just take the people who are overweight, what is the probability, and I'll write it this way, that you're younger than 25 years old, given, this is kind of a little symbol for given, that you're overweight. So out of all the people who are overweight, what's the probability that that overweight people are younger than 25 years old? So what you're going to be looking at here is now you're just restricting what you're doing. And you know what? Let's get the blue pen out just to sort of highlight what we're doing here. So, oh no, you know what? I'm doing this the wrong way. So here's the overweight people. I'm going to highlight it in blue. And we're just looking at them. So now the total we're interested on the bottom is going to be this 205. And we're saying, well, what's the probability here? There's 65 people who are less than 25 years old and are overweight. And there's a total of 205 people who are overweight. So that's kind of what you want to do for that one. And lastly, the probability that we're not obese. Well, now what we're doing is we're looking at everybody who is not obese. well, probably that we're not obese. But actually, interestingly enough, if you'll remember on, well, I don't know what page it's on, but when it comes by the law of complement, what you can do is the probability that you're obese or you're not obese is 100%. You can either be obese or you can not be obese. That's everybody in the world. So you can actually use a law of complement to make this easier for you, because you already know the probability that you're obese or that somebody in this sample is obese. So what you can do is you can say, okay, well, this is just equal to 1 minus the probability that that the person in your sample is obese. We already figured that out over here. So this is just 1 minus 190 over 410. Oops. So that's equal to 410 minus 190 over 410. Now what's that going to give me? Can't do math this late at night. 220 over 410. Okay, well, I hope you all enjoyed. If there's any issues or you see any inaccuracies and any other stuff, feel free to point it out to me. I'm going to try to do videos when I can. I just thought for this probability for contingency tables, you really have to see it in action to understand it. So I hope you've learned something. Hope this has been helpful. And yeah, I'd love to hear feedback. Have a good night.